much for coming, all of you. And I always love to, meet and talk to Preparedness at our irregularly scheduled meetings, either conferences in US or elsewhere. It's always a pleasure to meet you. So I'm going to talk about observing the terrestrial water cycle from space, and it would be, I would say, a buffet of different results. Rather than focus on one thing, I would try to give you a buffet of results, because there is a lot of progress has been made on this topic, and I'd like to just explain all of it together. So the motivation we have is the study of hydrology is important for science and society, and this is nothing which I have to emphasize to you. On page 9 of today's Bangkok Times, there's an article which says that because of sea level rise and because of the dams being built upstream, all the deltas in Bangkok, in Ho Chi Minh City and Shanghai are going to be losing sediment. There's a lot of articles, but it's interesting that I just read this morning when I was eating breakfast on page 9, written by somebody from WWF. So there's a lot of studies on that. Traditional hydrological studies using models and ground observations are limited in space and time. Satellite sensors, and because I want to emphasize on satellite sensors can observe things at over large areas and over long periods of time. But however, they have poor resolution and very infrequent temporal repeat. But we must improve the satellite sensor spatial resolution and gain better physical understanding by using satellite data in conjunction with ground observations and models. And at some point during the talk, I'll touch on each of these. So to start with, how do you represent the hydrological cycle? This one is a representation of the hydrological cycle using the land information systems. And you can see over here you have precipitation, you have radiation, both long-wave radiation and short-wave radiation. Then you have the water balance and the energy balance. Together you have evaporation, sensible heat flux, ground heat flux, and all kinds of exchanges of water and energy with the soil and the vegetation. So it's just a whole mixture of all these things. But just looking at this picture won't do us any good. We have to represent it. So in most models, this is how it's represented. And here, for simplicity, I'm using a 3-layer model. You can have as many layers you want in your models. The very interesting things of this are, the layers are coupled with each other. That is, the drainage from one layer goes to the other layer, from the second layer goes to the third layer. These drainages are driven by soil moisture as well as by the properties of the soil. So if you look at this and say, oh, this is pretty simple, I can do this analytically, it's not possible, because this Q12 is a function of θ1, which is the soil moisture of the first layer, and Q23 is a function of θ2, which is the soil moisture of the second layer, and so on. So it's coupled, it's nonlinear, and the best part is that the energy balance equation has this term ET, or evapotranspiration, and evapotranspiration comes from the transpiration from different layers as well as the bare soil evaporation. So if you think about it, the energy balance, the water balance are all a set of coupled, nonlinear, partial differential equations. So obviously we cannot just do it at the back of a piece of paper. You have to do it numerically just using a computer. So the case for satellite remote sensing, I mean, we just started talking about the importance of hydrology, but one of the things, if you look at hydrological variable observation, and Thailand is a country where you have a lot of observation, but there are some parts of the world, and I will come to those in a minute, there are limited sampling of precipitation, soil moisture, vegetation from in situ sites. It's limited because it's limited in spatial coverages. And if you think about something like precipitation, the rain gauges are at the flat areas in the lowlands. So there's seldom too many rain gauges up in the hills where it actually makes a big difference of how much water rains, because all that water comes down. And the problem is it is difficult or expensive to implement. Now, satellite remote sensing obviously offers you a very good idea of how to do this over large areas. Now, remote sensing has a long history. And you know, when you think remote sensing, everybody thinks of Landsat or MODIS or AVHRR, because Landsat and AVHRR are the long-term sensors. But for water, you know, the specific area of the electromagnetic spectrum which is useful is the microwave. So microwaves have been going on since 1978 from Simmer, and I'll show you a cartoon for that in a minute. But they are very poor resolution, 40 to 150 kilometers. So it's not a very good spatial resolution. So higher spatial resolution and more temporal repeat is always desired, because these days people are into precision agriculture, you know, hyperscale modeling, weather prediction, all which requires very high scale spatial resolution. Even 20 years ago when I was doing my PhD, you know, we were talking about resolutions of the order of 1 kilometer was a good idea. Now, you know, you can even start expecting people to ask for 100-meter data. So, you know, we'll be there. Now, where are we now? We are in a very golden era of remote sensing, and this tells you, and this has a whole bunch of sensors, that these are the hydrological variables. And if you start at the bottom, because the bottom is the part where, you know, we have the most data, from the 1980s we have Landsat, and Landsat is very, very important, because, you know, for any study you do, you can just pull the Landsat images for the last 30 or 40 years. And again, it may be a problem in some parts of the Mekong, because you know, we have less amount of clear days. You know, there's a lot of clouds in the sky, and that won't work if it's cloudy. And then you have AVHRR, which has provided vegetation index and surface temperature for a long time. And then we have MODIS along with it. And then wetness, as I said, that, you know, everything started with Simmer in 1978, and then we followed the SSMI. But the real part of hydrology came with soil moisture, and the soil moisture started with AMSER-E, followed by AMSER, SMOS, and SMAP. And then we have rainfall, and rainfall is really, really important. PRIM and GPM have been the workhorses of providing rainfall, and right now you have 20 years of iMerge data, and this is really, really good, and I'll show you examples of that too. Total water, very important. GRACE and GRACE-FO has made lots of news splashes all over the world, you know, but depleting groundwater all over the world, depletion in groundwater all over the world. And then finally, atmosphere. We also have a lot of atmospheric data sets with water vapor profile and air temperature profile. So if you arrange this all into a nice cartoon so that we can actually see this, this actually is published in the National National Academy's Decadal Survey for NASA, so you can actually find this online. You can see that there is a lot of different variables for the terrestrial hydrological cycle, and all of them have some sensor or the other. And the problem you will see here is that some sensors were in the past, some sensors are going to be in the future. Like, for example, one of the biggest things which is going to come in 2 years or so is SWOT. That will revolutionize everything. So you don't have to go and ask somebody in Cambodia for the level of Tonle Sap Lake. You can just look it up online. So imagine how strong that is. Or you know, the level of rivers which are wider than 100 meters. You know, that'll all be online. So that's one of the biggest benefits for hydrology coming down the road. And then we have soil moisture, and again here I write AMSER, it's the past, SMOS and SMAP are the present. So there's a whole bunch of sensors listed in this cartoon which are past, present, and future. And you know, we can't really say that all of these are available at the same time. But at the end of the day, you want to solve the energy and the water balance equations. So let me start with some examples, and each of these examples are from different students. I mean, I did not do any work. So first one is the temporal variability of vegetation, and one of my students who just defended his PhD, newly minted doctor from Iraq, wanted to work in the marshes of Mesopotamia, and everybody has probably heard about the marshes of Mesopotamia. There is 3 marshes, the Al-Hamar Marsh, the Central Marsh, and the Al-Huwaiza Marsh, and you're trying to see how does these vegetation changes. And again, this is a published paper as seen below here. So this is an example. Again, they're trying to pick up 2 dates, one August 1985 and August 1989. You can see 1985 has much more greenness, 1989 not so green, and these are all The same images are there in the paper. So if you look at it, and if you look at these marshes, you can almost divide this into three parts. One is the part between 1982 and 1993, before the ruler of Iraq diverted the water from these marshes because of political reasons. And you can see this marsh vegetation shows this wonderful ADPI pattern. And again, these are for all the three marshes as shown in that legend out there. And then once he disrupted the flow of water, because without water you can't have vegetation growing, you can see it all goes topsy-turvy here. And then since 2004, the villagers broke all those temporary dams and started getting water back into the marsh. And it's grown back a little bit, but some of my ecology friends tell me that the growth of the vegetation in this marsh is not an order of 5-10 years, but 30 to 40 years. So it will take many years for that to come back. So that's why we should be very careful when we have such human damage. It takes a long time. I mean, human damage can cause much more ramifications than climate change or other things. But this is how it looks like. And then if you analyze this, the whole point is trying to analyze this. And in these all three periods, the post-diversion period, the pre-diversion period, diversion period, and the post-diversion period, we can pick out this. This was 85, this is 89, and then 94, and then 98, etc., etc. We can do the analysis of how well the area responds to this flow of water. And again, as I said, that paper is in full reprint in what sense, published a few years ago. The second part of hydrology is soil moisture. One of the things which we all care about is soil moisture, because soil moisture is the central part of the hydrological cycle. Depending on the wetness of the soil, it determines how much water infiltrates into the soil or how much runs off into the river. So it's a very, very important thing. And soil moisture is like a memory. So if the soil is wet and then you have a lot of rains in the summer, then you result in floods. If the soil is dry and then you don't have rain in the summer or in the spring, then you have a drought. So soil moisture is probably one of the most important parts, and also very difficult because people don't go around measuring soil moisture. People measure air temperature or wind speed or humidity, but measuring soil moisture is a little difficult to do. And at most, soil moisture estimates from satellite data is at tens of kilometers. So it's not really very high resolution for people to understand. And if you take 10 kilometers, it's all the way from this building to one of those buildings in the distance. And giving you one number for this whole area is a little difficult when you are interested in understanding high resolution problems. So one of the things we did was we said, okay, can we take this 10 kilometer or 9 kilometer soil moisture and break it down into 1 kilometer boxes? And the way to do it is that if you take the daily average soil moisture and you take the difference in the temperature between the early morning and the afternoon, if you have a huge difference in temperature, that means the soil is very dry. And people who have been to desert climates understand this, that in desert climates, the difference between the air temperature or surface temperature early in the morning and mid-afternoon is huge, 50 degrees sometimes. Okay? But on the other hand, if you're going to the ocean, you realize this, that the difference in the temperature between 2 a.m. and 2 p.m. on the ocean, the temperature of the ocean water, is about 1 or 2 degrees. So more amount of water means less amount of temperature change. And you can apply this to land, but the only complication part in land is that you have different vegetation. And if you have more vegetation shielding the land surface, you end up with a difference in temperature. So it gets modulated. So what we did is we used 30 years of data from both NL- and GL- to make these lookup tables to create these kinds of tables, or to create these kinds of curves at 1 kilometer. And this is how it looks. You can see over here at 1 kilometer on the top, 9 kilometer on the bottom for different times in 2018 over continental US. And by the way, this data set is available. It's free. Anybody can use it. all you have to do is send me an email. So you can see over here, there are some parts over here which are blank, and that's not intentionally blank because we're using surface temperature. So if it is cloudy, we will not have coverage. And so this is a problem, and it's a problem for areas of the world where there is a lot of precipitation, convection, especially, and presence of clouds. But you can see over here that this spatial resolution is much higher. If you don't believe me, you can see on a smaller scale in the San Pedro watershed in Arizona, you can see that this is 9 kilometers. You can see this nice boxy structure, and this is 1 kilometer. You can see the spatial resolution jumps out at you. 9 and 1 is a huge difference. You know, over the US it's difficult to see because it's such a big area, but over a small area, the differences come staring at you. Now, we are not stopped just at soil moisture from SMAP or SMOS, but there's also some other there's also some other satellites, and one of them is a Cyclone Global Navigation Satellite System called Cygnus. And actually, this is not meant to do soil moisture. It was meant to figure out the speed of wind over the oceans, to figure out where the storms are going. But we have harnessed it to figure out soil moisture, and this is again another published paper in GRL. Not only that, the thing is that soil moisture from all these satellite sensors can also be used in a different way to figure out, I don't know why this keeps jumping, sorry, to figure out how the water is stored in the topsoil. One of the most important part in hydrology is how much water is stored in the soil. And this example gives you using different sensors, SMAP, SMOS, ASCAT, AMSR2, GLDAS, and ERA interim products to see the kind of histogram. And you can see similar, you know, all of those histograms seems very similar. And then this is the precipitation fraction, less and high. This is high, I'm sorry, the scale is not easily visible. So you can see how much water is stored in the soil. And you can see the parts where the dry parts has less water stored in the soil. The wet parts like east coast of US, Southeast Asia has more parts stored in the soil. And this is another analysis when people want to understand land-atmosphere interaction to see how much water is stored in the soil. And this influences the formation of the boundary layer, the sensible heat flux, and formation of clouds. So very, very important. And again, this appeared early this year in Water Resource Research. Now, I showed you one piece on vegetation, one piece on soil moisture, but you know, you want to bring these things together, and that's the whole point of hydrology. We don't want to do one thing at a time. We want to bring it together. And this particular paper is an integrated assessment of understanding that. Before I show you that, look at this, a very simple movie. The vegetation index from the Terra part of MODIS satellite is on the top left. Soil moisture from SMOS, soil moisture and ocean salinity sensor of ESA is on the right. And then precipitation is a combination of our trim and GPM over here on the left bottom part. And the liquid water thickness from GRACE tells you if there's more water or less water compared to an average. So you can see over here that the parts of this moving of the IPCC with more rainfall, less rainfall results in more soil moisture and more liquid water thickness. And this is only a 8-year movie. It's only till 2017. We are extending this to 2020 right now as we speak. So you can see over here the shrinking, the growth and shrinking of the vegetation. Very, very important, visualizing this, because we have these satellite data sets which are global. This is one of the most easy parts of doing this analysis. Now, coming to where we are living, right here, or sitting right here, the Mekong. So, if you look at these time series, and again, I'm not trying to say we're doing any prediction. If we look at the last 20 years, because we have had TRIM data since 1998, but we have only had GRACE, or the Gravity Recovery and Climate Experiment, since 2002. So if you look at this and try to piece together precipitation from TRIM, evapotranspiration from MODIS, runoff from GL dash, which is a bottle, and water thickness from GRACE. Just think about this. So you look at this long time series, it's almost 17 years. And we actually have added the new data from GRACE, because GRACE follow one. GRACE stops here, and this is GRACE follow one. Look at it and then say, hey, can I pick out some wet time and some dry time? Now, 2005 was a dry time. You can see the rainfall, negative anomalies. That negative anomalies translates into negative runoff anomalies, or very low runoff 2 months later. And then same thing with ET, very low, especially in the southern part, where we are, very low ET. And then very low amounts of water, total water storage in lakes, in reservoirs, in aquifers, etc. Now, fast forward to 2011, when it was very wet, September 2011, you can see this is the rainfall pattern, and all of these are anomalies rather than actual numbers, so it's a departure from the average. And then look over here, this is the runoff, which shows some parts, spotty parts of very high amounts of runoff, and again, some parts of very high amounts of ET. And then look over here, the best part is a couple of months later, in November 2011, huge amounts of water. So all the water ends up in the aquifer and makes this thing much, much heavier than in the past. So looking at this time series tells you a lot about extreme events. And as I said, that it's not like you're trying to predict anything from this, but at least you get to see that the positive and the negatives are easily visible from piecing together satellite data sets from different sensors. And this goes very well with that cartoon I showed you with that terrestrial water cycle. So here we're not using just one sensor, we're using TRIM, MODIS, GRACE, and a model. So you can see that putting it all together makes a lot of sense. Now if you take the same thing for the Murray-Darling River Basin, which is also a very important part of the world, and you can see again, August 2009, low rainfall, low ET, low runoff, low total water, and the same thing for 2010 in the opposite. So this tells you very nicely how easy it is to look at these data sets. And this is not, as I said, this is not some big analysis, but it's more to do with putting the pieces of the story together. Now, one of the things which we all deal with is droughts. In southern India, in the early part of July, there was a huge drought. And if you look at it, this was an aqueduct. There's no water. There's an aqueduct, but no water. These are the fields which are completely parched. This is the lake which supplies water to the big city of Chennai. And then these are people lined up to get water. And this was, I think, in mid to late July. And then 2 weeks later, there was a huge rain and everything, got flooded. So you can imagine they went from no water to complete water within 3 weeks. And, it was another big disaster. So if you look at India, and this is a part of the water anomaly, and we're just showing you this, let me show you this picture here. So the three river basins here I'm showing is Indus, Kaveri, and Ganga river basins. This is the GRACE total water storage anomalies in millimeters, and you can see the follow-on data is at the end part of it, because GRACE follow-on starts from summer of 2019, sorry. And then you can see that these Indus declining trend, Kaveri reasonably straight horizontal, but the Ganga river basin you can see over here. But we've had more rainfall recently, so more data. So more. So you can see that this is an easy way of looking at this changes of the variability in the water cycle. Now we have gone off and done the same kind of maps or same kind of analysis as I showed you for the Mekong and the Murray-Darling River Basin, and looked at this long time series from 2002 to 2017, and looking at the wet and the dry seasons, and looking at how the precipitation, runoff, evapotranspiration, and total water all co-vary with each other. And this is very important because these are data sets which we have, and putting it together is a very simple aspect of the analysis, but the knowledge learned from this is actually immense. Now, if you go to another simple, very, very simple analysis, and all of this is in the paper in Journal of Hydrology, which I'll be happy to share with you, but it's also online. Everybody knows that the Amazon River Basin is a very wet, very water-rich river basin, and everybody knows Murray-Darling is an example of a river basin which has little or no water. So you've seen Amazon, very nice, very lush green forests, and you've seen Murray-Darling. Most of the time the river basin looks brown, and it's intensely managed, and a lot of agriculture in Murray-Darling River Basin. But if you draw a very, very simple curve, you'll realize why this happens. So all I'm doing here is plotting the same index. The index is called the monthly rainfall anomaly index. You take the monthly rainfall anomaly and divide it by the monthly climate. So it's a dimensionless quantity. And you can see over here, the Amazon River Basin, the fluctuation of this index is very little. It's less than minus 0.25 to 0.25. So it varies in a very, very small area. Whereas on the other hand, if you go to the Murray-Darling Basin, it's a huge variation. It's -1 to +2, and over here it's actually +3. Huge fluctuation in the water. So the rainfall coming into the catchment varies by huge orders of magnitude when you compare it to the average. As a result, sometimes you have too much water, sometimes you have too little water. So you can imagine that as a river basin, Amazon, it's much easier to plan because you know there is water and the water will not vary too much. But on the other hand, the Murray-Darling Basin is like the water goes up and down. So the planning for the hydrology is much easier in a place where the fluctuation in the rainfall is in a manageable position. So you want things like this to understand and plan for the water resources. One of the things when we talk about rainfall, as I told you, one of the most difficult parts of rainfall is the fact that you do not have enough number of rain gauges. And that has been our work for the last few years, especially working with ADPC and people in Southeast Asia. Everybody knows what kind of data we have in rainfall. This is like a undergraduate hydrology class. You have a rain gauge, you have a radar, you have a satellite. I mean, in the best of all worlds, you want to have all three of them all over the place, so each of them checks and balances on each other. And we know that having rain gauge is very expensive. You have to keep it, you have to maintain it, you have to have a telemetric system to record the data, and you have to make sure it's working properly. Radar is okay. This is things which are there at airports, it's there at television stations, etc. I think maybe this one doesn't have it, but you can see a big golf ball on the top of buildings, and that's a weather radar. Satellite is there all the time, and it gives you some amount of data, but again the spatial resolution is very, very poor. Here, this is a point. This is normally 1 kilometer. This is few kilometers. So you can see that you have a trade-off between the convenience in a satellite. On the other hand, this is very precise to the point. So one of the things we have done, and this is not just for Thailand or Vietnam, but we have done an analysis of the rainfall in the lower Mekong River Basin. So we have taken all these gauges. There are a few thousand gauges, and these are all put by dots, and then we have taken rain gauges, 477 actually in the Mekong River Basin. We have taken two data sets. One is the TRIM multi-satellite precipitation analysis TMPA version 7, and another is CHIRPS, which is the climate hazard group, infrared precipitation vegetation data, two very, very standard data sets, and try to see how they match up. And you know, we've done a lot of this work. This work is actually in re-review, so hopefully it'll be published soon. One of the things which is very important when you do these things, and especially when you are doing comparison between rain gauge, radar, and satellite, is this very interesting index, and this is not something new. I didn't do this, it's been done since the 80s, is rain, no rain. So when this rain gauge is saying it's raining, does the satellite say it's raining as well? So rain, 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 no rain, no rain, rain, no rain, no rain. So, you know, it's a very simple method. And we did a big time analysis, and you can see over here that each of them have their own quirks. And again, chirps, you know, having no rain is very, very important, and TMPA does a little better than that. But the whole point of using satellite products, chirps is also a satellite product, is trying to see the seasonal variability, especially on a spatially distributed scale. So this looks like how you could see from trim. This is from chirps for the dry season, wet season, and an annual cycle. And again, this is about 20 years of data. And you can see over here, we also put the rain gauges with their numbers in same color coding. Again, rain gauges are a point. And you know, I think it's a reasonably good job. And to see the actual statistics, this is the table. Not only did we look at this rainfall comparison between chirps and rain gauge and trim and rain gauge, but we also did some kind of understanding in is the heavy rainfall overestimated or the light rainfall underestimated, etc. And you know, we whole bunch of stuff for you to look at here. Another very, very important aspect in these areas is the biases we have with elevation, and that's very important. If you have elevations over 1,000 meters, you know, in the high mountains, you don't have much sites. You only have 12 stations. Okay? And so the R values or the comparison, the biases, all, you know, go all over the place, and it's very important for you to look at it. And the fact that over 1,000 meters you only have 12 stations tells you that we may not be able to believe it. Okay? And again, we are comparing a trim which is a 0.25 by 0.25 degree pixel with a single or two rain gauges in that pixel. So how representative is also comes into question. Chirps is a little better, is 5 kilometers by 5 kilometers, but still 5 kilometers is still too big of an area. So, you know, hopefully this paper will be coming out soon and you can read it. Now, having this rainfall is only one step. The second step is how do you harness it in hydrological models. So we've been working in using not just trim and chirps, but a whole bunch of data sets in what we call SPE, Satellite Derived Precipitation Estimates, and see, hey, how does it simulate stream flow? Because at the end of the day, you want stream flow to be simulated properly. And this research question is, do current gridded SPE products agree well with precipitation measured by a rain gauge? Is there any difference in the performance of different precipitation products as inputs to the SWOT hydrological model? You know, the SWOT is a model which many people use all over the world, soil water assessment tool, and feeding it with rainfall from a rain gauge as opposed to satellite product. Which one is better? So, one of my students has been working on this. This is a paper which is, you know, now in revision. So we have 6 watersheds for 6 different climate zones in Vietnam. 1, 2, 3, 4, 5, 6 sites, 6 watersheds. We have stream flow data. We have rain gauges at 31 stations, and you can see, you know, the stations are marked in this red over here, and then we do a whole bunch of simulations. So this is how it looks like. We're using 6 different products of satellite precipitation estimates, and this has different spatial coverages, different temporal resolution and spatial resolutions. And as I said, chirps is the best because it has 5 kilometer spatial resolution. Of course, the rain gauge is the best, it's a point, but you don't have too many rain gauges. And these are different watersheds. I think the Shala watershed is the biggest watershed, and each of these watersheds we have tried to put a little grid to show trim versus I-merge versus chirps. You can get an idea of how many small boxes fall into this watershed. Because at the end of the day, we have to put these rainfall values into the SWOT to simulate the stream flow. But this is really, really exciting. So this is how the intercomparison between rain gauge and SPE products, and again, all of them are listed out here in the dry period, the wet period, for probability of detection, and a whole bunch of other metrics, which for most of it, the gauge corrected I-merge final product version 6 exhibited the best thing. So I-merge is this latest product from NASA. It's available for the last 20 years now. Now, the SPE-driven simulation using I-merge version 6 shows a very, very good thing. So, and again, I won't bore you with this map. Again, it will appear in the paper very soon, hopefully. But look at this. The I-merge version 6 compared to the gauge. If you just compare this one and this one, if you look at this part is calibration, this part is the validation. So the Nash subnet efficiency, about 15% better or 20% better. The p-bias, 4.3% as compared to 25%. So you can see that using the satellite precipitation estimate from the I-merged final version 6 data set shows very good. Now, there's more results. I'm not going to bore you with the more results, but for the other river basins, when you have a very small river basin, and if you have 2 rain gauges, it's probably captures the precipitation in the basin very well. So you're not going to win an argument saying that, oh, we will do better than any rain gauge. We will do better than the rain gauges when the rain gauge network is sparse. When the rain gauge network is dense, sure, rain gauge will do fine. But for most part of the world, either the rain gauge network is sparse, or B, somebody will not give you the rain gauge data, or 3, which is most likely as well, is the rain gauge data is not correct. So you want, in all 3 of them, I think having an independent set always helps. So this is very exciting. It's very exciting. Again, we want to examine this over a whole bunch of other things. And again, so the GPM I-merge final version 6 exhibits the best results. And again, we're not talking about just comparing rainfall, but we are trying to see beyond just rainfall in hydrology, because we don't really care about just comparing rainfall, but we do care about what the rainfall can do. This is a really, really important contributions. So then it brings about to a very interesting paradigm. People use this word, at least in US, it's a big word, big data. And all of us work in big data just using precipitation, and we're just talking about a few sample products. I'm not counting all the products in the world, but if you look at it, the required storage for daily database in gigabytes, it's like, you can see it's 3,500 if you accumulate it up for just the last 20 years. And again, I'm not counting all the data sets. This is just a sample of it. So very soon you can fill up a whole bunch of hard disks or petabyte hard disks easily using this data set. So there is a problem that you do have to worry about data storage, data accessibility, and all the new versions, how you access data and process data are very important. People call about cloud computing, AWS or Google storage, whatever. You probably need more of it as time goes on because we have so many data sets. Now, I'll spend the last few minutes talking about, my association with ADPC and SERVIR. We were part of a big project which Pierre knows very well with NASA Goddard, USAID, and ADPC and called SERVIR. Couple of the products which have been developed by the PI of this project, John Bolton, has been, one of them has been the near real-time flood detection and socio-economic impact assessment in LMRB. Very, very important, because if you can detect the flooding, it's very important, because most of the people in this part of the world, economy depends on water, and economy is destroyed by water if you have a flood or a drought. And John and his two people who work with him, Akash worked with him, Perry and Akash, they have worked to create this kind of flood detection. Another part, which is the value of economic impact. Everybody now cares about, what's the value of information. Value of information is a very, very interesting metric now. What's the value of information? And this is an example of value of information, which is value of near real-time Earth observations for improved flood disaster response. So if you have that data with you, how much can you benefit people? It's not just research anymore, it's to help the economy. And this is an example of a near real-time Earth observations used to produce flood impact assessment of a flood event in Bangkok, Thailand. For 9 minutes, saving of 9 minutes, you can save over $52 million a year. And again, this is based on one of the estimates, and I think this has been also published, if I'm not mistaken. The third one is a part where I was a part of this paper. I think there may be the paper list here, which is missing. It was published in Remote Sensing, trying to use satellite data, data for rainfall, and show that in this catchments in the lower Mekong River Basin, you can do much better simulation of runoff using SPE. And nothing strange, because we did the same thing over Vietnam as well, but this is for lower Mekong River Basin. Another work which has been done and published is the land cover classification. I told you that one of the biggest impact humans do for hydrology is changing the land cover. And people have been changing the land cover for a long time, and changing the land cover can change hydrology just like this. You don't have to wait for climate change to come, it will change tomorrow morning. And people fail to realize that knowing exactly how the land cover is positioned is more important than trying to figure out rainfall or runoff or soil moisture. And this is something that Joe Spruce and John have been working on. So 2 years ago, we all looked a little young. I think Pirnan looks the same from 2 years ago, but we all looked a little young. So we came here, we exchanged ideas and did stuff. And there is a lot of different tools which ADPC, SERVIR, and NASA Goddard are exchanging with each other. These are all tools online to work out things. So I should not forget to say who funded this work. People from NASA headquarters, Jared Enting, Terrestrial Hydrology, Brad Dorn, Applied Sciences and Water Resources, and Nancy Serby, who leads the Applied Sciences program in SERVIR. And again, as I said, I don't do anything. These are people who do it. We are John, Ben, Jessica, Hyun, and I always love to say this saying, because when you talk about NASA Goddard Space Flight Center, it's named after a very important person, Robert Goddard, who invented the rocket. And his quote was, "It's difficult to say what's impossible, for the dream of yesterday is the hope of today and the reality of tomorrow." So the next time you paint this room, you can put up that saying on the wall too. So, final thoughts. Again, as I said, I just gave you a buffet of different ideas which use remote sensing and help hydrology. Certainly not the only ones there, it's the ones I know best because I've been involved with them. So satellite remote sensing helps us to estimate a better picture of the Earth system. This does not imply we stop collecting in situ observations, because in situ observations are very important. In situ observations are the cornerstone of calibration and validation of algorithms, as well as calibration and validation of models. Very, very important. You cannot just stop doing things, but you have to do more of it. With increase in population and climate change, global water resources is one of the most important research areas. So, water resources is probably more important. As I said, page 9 of Bangkok Times has an article on sediments in the Mekong and the lack of sediments, because you build more hydropower dams, then there'll be no sediment in Bangkok, Ho Chi Minh City or Shanghai in a few years. And combining, and again, you can't use one part of research and not the other, but combining observations, modeling, and data assimilation will lead to better estimates of available water. That's very, very important. You cannot do with one or the other, but doing all of them together is the right thing. Thank you very much.
The floor is open for questions, thoughts, comments, anything for Venkat.
I have one question. You mentioned in one slide about the downscaling techniques. Okay. You mentioned in one slide that about the downscaling techniques. Would you please explain a little bit on the technique that they use?
Sure, of course. So what we do is, this is a published technique and the data is available. So what we do is we take the day-night surface temperature and prepare these lookup curves. This is like a curve. For any particular part of the world, you make this picture using the model. Not. So the day-night surface temperature difference. You know the average daily surface temperature, average soil moisture, and for different vegetation indices, you make up this curve. And then, knowing the exact surface temperature at that time from the observation, you go to the correct value of the vegetation index, which is there at that time, and you get the soil moisture. Now, that's the 1 kilometer soil moisture, but you have a 9 kilometer, let's say. So you have 81 boxes. So you average all these 1 kilometers over 81 boxes and make sure it's unbiased, because it cannot be biased. So the average is the same thing which is observed by the satellite sensor, and then you produce it. So we have written a big paper on this, and we have done validation, because without doing validation we cannot prove anything, and we have a lot of results on it. So you end up with this kind of 1 kilometer soil moisture, and we compare it to, in the United States, we have done a lot of this, because there's a lot of data sets available to do it. It's called SCAN, Soil Climatology Analysis, Soil Climate Analysis Network, SCAN, and it's the USDA sites. So it's about 1 to 2 sites per state, and so we have compared it to many of these sites, and we have shown that our 1 kilometer product actually does very, very well. It actually does better than the NASA's official product. So we have a very good algorithm.
So you mean that they have only data for United States?
Yeah, USDA has only for United States. So if you have data in Mekong, we can use it for that validation too. But collecting the soil moisture data is a little bit more cumbersome and expensive, and it's not there all over the world. There are some sites, and they're going to do that.
So do you have any idea that if you really want to have some sites in the field?
Yeah.
How many? It should be appropriate.
So that brings about the statistics. So if you want to compare the soil moisture from a 1 kilometer sensor to the sites. I think the rule of thumb is 3 in 1 kilometer, but if you have a bigger box of 9 kilometers, there is a lot of networks which in US actually exploit this kind of relationship, and the easiest one to compare to, if you want to set up your own thing in the field here, is a strategy in US called Texas Soil Observing Network, TXSON. And so they have many of these things, and they're actually comparing it with them. So yeah, you can, absolutely. Okay. But the problem is, it's not just the number of sites in a box, but also you have to have this over a long period of time. Doing it for 1 month is not enough, maybe 5-10 years. So, okay. But in US, we have some of these which are very good sites. Some, the USDA scan is 1 site in 1 kilometer box. So it's obviously not perfect, but it's better than nothing. And they're actually doing the same thing. One of my students is doing the same thing of downscaling for the whole lower Mekong River Basin for the last 4 years. And we are getting some results right now. If you come to the AGU fall meeting, you may be able to see that.
Question.
Yes.
Sorry, I didn't join you since the beginning, so I'm not sure that you have covered that. You probably have covered that thing already or not, but probably my question is, I guess that you have the summary of your talk. It's about not to stop collecting in situ data. So that's very good actually, because my question is like, developing country like Thailand in some basins or sub-basins, so we don't have enough, or the density is not quite sufficient actually for the rain gauge and everything. But your work showed that we can probably assimilate, maybe the key to the data assimilation is to use the local with the global data set, so that we can better estimate or maybe do some predictions, things like SWOT analysis and things like that. So what's, I guess that probably the idea is like you use the local in combination of assimilated with the global to get some optimized or maybe the optimal numbers of rain gauge in some kind of sparsely gauged basin, or to optimize the numbers of the density of the station. So could you, share your thought on that one, or?
What you said is perfect. So basically why you need in situ observations is that the in situ observation will serve as like some benchmark to characterize the, I hate to use the word error, but in the assimilation you have to use an error covariance. So you will not be able to do the error covariance in assimilation, let's say of soil moisture, if you did not compare your satellite product with some ground-based products. So comparing them and getting the error covariance is the first step to assimilation. So that's why you need these in situ networks, and especially as I showed you that in a small river basin, actually having 3 or 4 rain gauges is probably better than using a satellite product. And that's good to know. It's good to know that you cannot use satellite everywhere, but you can only use it in places where it has more information content than the local data. So if you wanted to know the rainfall right behind your house, satellite probably won't do anything. Having a rain gauge is much better, because that's the local information. So it all depends on the scale you're working at. And you said correctly, having this global information and assimilation at global scales give you some information which can be interpolated to local scales.
Yes. And talking about scale, actually, so we have problems with using satellite data, because satellite you said a few kilometers, but in the case, I'm actually interested and have been worked on GRACE, analysis, to try to get some groundwater storage change in our country. And as you mentioned that the limitation of the satellite is scale, so it's not localized enough. So right now we have collected some data in the at the local scale, so that we try to probably downscaling GRACE and maybe look at the accuracy of the satellite derived products, with to estimate some local fluctuation of the groundwater in our area. So would you share some thought on how would we do that, and how what's the better, maybe the best way to deal with the local data and scale?
So there's been a lot of results on GRACE, but GRACE inherently their spatial resolution is about 500 kilometers, so you cannot do it on a small basis. So the kind of results I showed, trying to do precipitation minus evapotranspiration minus runoff exchange in storage, is a first cut analysis. Then secondly, as you talked about assimilation, trying to use GRACE along with the data sets which are generated from model outputs is probably a best idea, because so the models actually will provide you with outputs at a much higher resolution than 500 kilometers. So then if you can interpret that 500 kilometer GRACE signal in the light of this high resolution, it will give you an idea of how to, and there are people actually who are doing this and trying to assimilate GRACE into models, and I think that's the way to go, because you cannot really model, I mean it's also difficult to model groundwater at a very high resolution because you do not know the stratigraphy of the subsurface to begin with. But
Just give us the
big picture. And sometimes big picture is enough, because if you're thinking about the whole lower Mekong River Basin, the big picture GRACE is enough. But if you're looking at the smaller river basin, then obviously you need much more than GRACE. I mean, as I said, even for rainfall, I mean, GPM is at 10 kilometers. It's useless for rainfall behind your house. So it all depends on where you are working.
So when you talk about your lower Mekong River work, is that maybe stem from the limitation of the data, that because we share the transboundary river, so that we are downstream or midstream, so we don't have data to do some simulation?
So actually that paper, which was published 2 years ago, it has the data or the analysis for not just Mekong or Murray-Darling, but for 11 river basins all over the world. And I didn't have to go to ask anybody data, because it's all publicly available data, but it shows you very nicely how things vary with time.
Continuous flow.
Absolutely, yeah. Yes.
So regarding the downscaling, so you mentioned that you have used the vegetation as one of the parameter. So even for 1 kilometer, like the vegetation patch within that 1 kilometer might be small.
Heterogeneous.
So was the vegetation fraction within that pixel considered?
No. It's too complicated, because I have surface temperature at 1 kilometer and I'm using vegetation at 1 kilometer. If I have surface temperature at a higher resolution, I can do it at a higher resolution. And actually we have done it experimentally using VIIRS. Don't ask me what it stands for, because I thought I knew what it was. So VIIRS is a visible infrared sounder, VIIRS. So we have done it at 400 meters and we get great results. So the higher resolution of vegetation is not enough. We also need surface temperature, because that's the thing is. So yeah, we can do it. We can, but the higher resolution is better. Higher is always better. But again, you can do it only on a small area. So remember, in a satellite sensor, the higher resolution means lower temporal repeat. VIIRS is 400 meters, but its repeat is only a few days. MODIS is 1 kilometer, is 2 times a day. So.
Question?
So I'm just wondering why you pick SWOT to, the SWOT model, soil, water.
No, I mean, I think, to be honest, I think most hydrological models are similar. There's not too much variability in a hydrological model, and in the end of the day, it's more how you calibrate the SWOT model and how you use it, rather than what model it is. I mean, yeah, you could do this with another model too. It doesn't matter.
And can any of these remote sensing techniques help with doing some analysis of the low flow, like the base flow analysis, things like that? Can you kind of give us some idea on that?
So base flow analysis, the easiest way to do base flow analysis is to separate the base flow in a hydrograph and then look at the rainfall and see the relationship between the two. So in base flow analysis, one of the most important things would be figuring out the rainfall, because low rainfall corresponds to base fall. So yeah, we can do that using the rainfall.
I'm going to ask. I'm going to ask something probably which is going to sound very naive at this point. So we were doing this study in India, which was looking into drought-like conditions, wherein the government wasn't too willing in some of the states to say that there are drought-like conditions. Essentially, the year was that of a rain deficit year, and what the government was essentially saying is that there is enough subsoil water to tide over the conditions. Now, my question is fairly simple, probably. Is what is the impact or effect that subsoil water would have on soil moisture, and what impact does it have on drought-like conditions?
So I don't know what you mean by subsoil water. Are you meaning how much? How deep? 2 meters, 20 meters, 200 meters?
The water that is always there, like from ages, underground water. So
You mean groundwater?
groundwater.
So yeah, I mean, the whole point, most parts of the world are pumping groundwater, I mean, US included. And the problem is that the recharge is much lower rate than the pumping rate. So if you're using up water at a faster rate than it's recharging, that old water is gone. And when it's gone, it'll take many more years to replenish it. So what what you're talking about is political, which I don't really have an idea about. The bigger problem is that if you can pump groundwater, you can pump groundwater from 20 meters today. Tomorrow you may have to go to 200, and then you could go to 2,000. I'm sure there's water everywhere, but the problems start occurring when you have to spend more energy and as a result more money to pump the water. That's the whole point. I mean, there's probably water, up to significant depths, and there's no mapping tool right now, as far as I know, which can tell you how much water exists in the subsurface. Only thing we can say is how much is it changing. Grace only tells you the change. It doesn't tell you how much water there is. So if you go deeper and deeper, you can pump more and more. But you'll run out of it, and you may also run out of economical solutions, because it's easier to pump water which is closer to the surface.
Any other questions? Still digesting a lot of information. Okay. I suggest to exchange business cards with Venkat.
I'll be happy.
Venkat, if you can put your email address up on the screen too.
Sure.
So people can because I'm sure some other question will come up later on.
That's my email, so I'll be happy to. And I have a few business cards, so I'm happy to work with it.
If you don't mind, we have already collected your email address, so we'll put on another list.
Sure.
In case we have some future seminars or events like this, I hope you don't mind being extended invitation.
Of course, I know she's in.
Okay, with that, let me thank Venkat again for coming all the way from the US. He'll be on his way to Cambodia.
Yes,
And maybe a little vacation in between. But Venkat has been a strong and very valuable partner of ADPC and organizations in Thailand. So hopefully you can establish contact and connection with Venkat. If you have any research questions, feel free to shoot an email. So I'm sure Venkat will be happy to assist on anything that you have. So thanks
Thank you so
again.
much.
So
Thanks, and
Thank you so much.
you can come back anytime.
That's it.